Okay, so what do we have here? So the first thing he does, and let's see, how much can I zoom in on this? Maybe to there. Okay, so the interesting thing is that data I just showed you at the end, it turns out there were almost 400,000 lines of data.
Wow.
So what's your first reaction to that? So if I go back to the data over here, which probably isn't on camera super well anymore, but it's 400,000 lines of data. Look at that, look how much I scroll down. So what do you think? What kind of problems do you think that creates?
Well, you're going to need to make something that can interpret that data, like decode that data. You have the numerical code, and you have to have something that figures out what that means, and probably figures out what it means fairly quickly.
Yeah.
Because you have so much of it.
Yeah, you have so much data. So what problems do you think that's gonna?
Well,
do you think?
If there's like one error in like the code, then the thing you might not be able to interpret it, might like glitch out.
Yeah, there could be data glitches. Yeah, that's a hugely important problem when you're studying large amounts of data. The other thing it means is we need to use a computer to look at it. Because if I asked you to just draw it out on some graph paper,
It would take a while.
yeah, it would take a while. So the data set consists of 13 columns. The first is a string of digits encoding the year and something that is almost but not quite the Fips code for the county. So that's some code for the county. So I guess it's just the year and the code, but they're lumped together.
Alright.
Do you know what a string of digits is? He says string of digits right there.
Well, it's just like kind of like a line of digits.
What do you think?
It's just like a sequence of numbers.
Yeah, it's a sequence of numbers, but
0 to 9.
the number itself doesn't matter.
Yeah.
But the problem is, if we try to interpret that as a number, what problem do you think we're going to have? Remember back in the beginning, and again, this might not be on camera, but the first one we had, it's a little off camera, I'm not going to change that, 01001, da 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 da. What if we try to have a computer interpret that as a number, what's the problem going to be?
That starting 0 is going to cause an issue.
Yeah, the starting 0 is going to make it just probably ignore it, right?
Yeah.
So that's going to mess up, but that starting 0 helps describe the county that it's in.
Mm-hmm.
So when he reads in the data, so he says he has to read in the data, and then he has to say there's a string in it, and then there's some real numbers in it.
Alright.
Okay. The data set consists of 13 columns. The first is a string of digits, and then that's the Fips code. The next 12 are the monthly average temperatures in degrees Fahrenheit in that county. For clarity, I like to add column headers, so he just describes the data, and we'll get to that. I'll show you what change that makes. To correct the Fips code, so this would be something where you would have to do some research offline to figure out what did that code mean.
Mm-hmm.
Okay, so he goes and gets that. But interesting, it looks like Mathematica already has that. So there's a Mathematica command called Fips Code. So I don't even know what that is. I'd never heard of it before this, but it's already in the Mathematica language. So that's nice. Now we add a column to correct the Fips code for each county. So you can see what he's doing here. He's taking his data set, and he's creating a Fips code out of it, and then he's also creating the year out of it, which says take the string, and then we're going to look at some code. And what do you think that -4 means?
It's probably the last 4 digits.
Okay. So why did he do the last 4?
Well, that's the year.
Yeah, so Mathematica actually had a nice, simple, I mean, this is only like a few lines of code, right?
Mm-hmm.
That it extracted those last 4 digits and also took the first digits out. And so now his data is broken out, so it has the year and the code. And then he just goes through and identifies just cleans up the data a little bit more. In order to take the average, this was interesting, to get the average for the year, which was what he was doing, he looked at the months, and he just did a weighted average. So January had 31 days, February had 28 days, plus one more if it was a leap year. And then, the number of days per month, and he did what's called a weighted average. So if January was warmer and February was colder, you wouldn't want to just average January and February.
Yeah.
You needed to average 31 days plus 28 days. So that's all he's doing there. And then this was interesting. The file includes data for the first couple of months of 2019, so I stripped it out. So what do you think this command means? C data equals C data, select year less than or equal to 2018.
Well, it takes it in, like, essentially selects the data from the first that is collected to 2018.
Yeah, so he just said, hey, I'm just want to ignore all the data that's later than 2018. And then one thing I was confused by on this next line, this was the one thing important, this is one important thing I couldn't get to work. He was looking at the moving averages. He took the last moving average of the temperature, so that's up to 2018, and subtracted the moving average from starting at minus 100. So that was confusing to me. So in my code, I just do the last minus the first.
All right.
And then he just, this is the most complicated part of the code where he's just setting up the color schemes. But that's all this is saying, hey, let's set up the color schemes.
All right.
And then he makes the graph down here. And there it is. So it's surprisingly simple. I would have had absolutely no idea how to do this, and yet he lays it out in such a nice, easy way. It's easy to follow. It's not so easy to create, but it's easy to follow. So now let's go through that data, or the code, I mean.